going to talk about trapezoids and kites. Trapezoids and kites. Please make note of both the location that you are watching this video, be specific, as well as the date and time. The location and the date and time. We're going to do a review here. We're going to follow brain and hand techniques where you're going to finger track, read, highlight, underline, draw, label, list, and we'll see what we can do here. It says we're going to draw a square PQRS. We're going to draw in the diagonals PR and QS. If the length of the diagonal is 12 PR, find all possible segment and side lengths and the measure of all possible angles. Okay, so let's recap here. From our family tree, we know that we have a parallelogram, and from a parallelogram we got both rectangles and a rhombus, and when you combine a rectangle and a rhombus you get a square. So a square has all the qualities of a rectangle, a rhombus, and a parallelogram. Keep that in mind. So it's PQRS, PQRS, and we're told we have the length of P to R is 12. So P to R is going to be 12. Now you want to draw in the other diagonal as well, S to Q. Keep in mind that's all the way. So this 12 I'm going to put right in the middle here, so we don't think it's only a piece here. So the whole thing is 12. Knowing that, we're basically supposed to find everything. Well, keep in mind it's a square. So let's start marking what we know about squares. Squares, like a rectangle, squares have 4 right angles. Also, like a rectangle, the diagonal length, so the diagonal length PR equals SQ. So if PR is 12, SQ must also be 12. So that's something we can find out. And like a parallelogram, the diagonals bisect each other. That means they cut this 12 in half, so this is going to be 6 and 6. We know the diagonals bisect and are of equal length, so this must be 6 and 6 as well. Now let's focus in. Like a rhombus, a square has all equal sides. So this, and this are equal, like a rhombus. So once we find one, we have the other. So let's see what we can find here. We have a 90 degrees, and also like a rhombus, we can cut those corner angles in half. So if we take that and cut it in half, we know we have a 45 and a 45 here. Opposite angles are equal, so this is 45, and this is 45. That means this is 45, and this is 45. And lo and behold, this is also 45, and that's 45. Let's see what we have here. Do you hear all those 45s? Now remember, the diagonals, like a rhombus, also are perpendicular, which means there's a right angle in here. If you watch very carefully, if you trace that with me, I'm going to wait for you to trace it. I want you to figure out this triangle, this yellow triangle that I just traced. It's a very special kind of triangle. What kind of triangle is it? You should have noticed that we have here a 45, 45, 90 triangle. Let's pull it out so we can see it here. There's a right angle. That means it's an isosceles right triangle. So there's 6 and 6. You guys know in a 45, 45, 45, 90 that the legs to the hypo is times by root 2. That means this length on the outside is 6 root 2. Since a square is like a rhombus, we know that all 4 sides are also 6 root 2. So if you notice in a previous lesson, we figured out just by saying something's a rectangle or a rhombus, or in this case a square, there is a lot of information that you can get from that diagram. That's why it's important to memorize those properties. So we have two more. And they are what's called a trapezoid and a kite. Trapezoid and a kite. Let's recap here and ask ourselves this. And this, I want you to actually have your own original thoughts. I'm going to be looking for this when we do our video note sign-offs. This is a trapezoid. This is a parallelogram. I'd like you to look very closely from the trapezoid to the parallelogram. And I'd like you to write a sentence or two. How is a trapezoid on the left? How is it different from a parallelogram on the right? Versus. How are they different? I'd like you to think about it and write one or two sentences right there. How is a trapezoid different from a parallelogram? Look at those, analyze them, and write a sentence. Okay, let's look specifically at a trapezoid now. A trapezoid, by definition, a trapezoid only has one set of parallel sides. Those parallel sides have a name. We call those the bases. So we would call this a base and we would call this a base. Traditionally, we would number the bases. We would call one of them base 1 and one of them base 2. It really doesn't matter which one is base 1 and base 2. That's just the traditional format there. And then the non-parallel sides, the sides that are not parallel, we call those legs. So this would be a leg, and this would be a leg. The angles connected directly to the bases, this angle here, and then these angles here, these are called base angles. Base angles. So when they're positioned right along the base, those are called base angles. That's the basic anatomy of a trapezoid. Now, trapezoid so a normal trapezoid has parallel sides, and then you have two legs. Now, if your two legs become exactly congruent, you have parallel sides, and now these two legs become exactly congruent in length. That's called an isosceles trapezoid. So be aware, not all trapezoids are isosceles. But if the legs are equal, we would call this an isosceles trapezoid. Now it has some special characteristics. One of the special characteristics in an isosceles trapezoid is that those base angles become equal to each other. Now there's a couple other things I want you to notice about a trapezoid. Here we have a side length AD and a side length leg, a leg BC. And we have the bases AB and the base DC. So this would be a trapezoid, and the bases are parallel. So we're going to go like this. Bases are parallel. If you were to find the midpoint of A to D and mark it, that would be considered E in this case. Put hatch marks around it. That represents E as a midpoint. E, in this case, would be a midpoint. If you go on the other side, we can make F is also the midpoint of B to C. using double hatch marks because it's our second midpoint. This segment that connects midpoints has a name. It has a name. If we mark E as the midpoint and F is the midpoint, if we connect E to F, physically connect E to F, that has a name. That is called the median. When you connect the midpoints, that is called a median. A median of the trapezoid. It has a secondary name. You might see it in other textbooks. That could also be called a mid-segment. A mid-segment. So median and mid-segment are the same thing. Let's check out some math here. Let's check the base units of A to B. Let's count those together. Base units. We're just going to bunny hop them. So starting from A, we have 1, 2, 3. We have 3 base units. And now let's do D to C. D to C. Put your pencil on D. Bunny hop. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. Now I'd like you to average those bases. Average those. Let's see what happens. We're going to do 3 plus 9. We're going to divide by 2 and see what happens. 3 plus 9, of course, is 12. Divided by 2, we're going to get 6 units. Now I'd like you to directly count the length of the median. Bunny hop it. Directly count the length of your median, E to F. We're going to bunny hop 1, 2, 3, 4, 5, 6. So what we have discovered here that the median is itself 6 units, which is the same as, I'd like you to underline average and basis. This is a very simple observation. We can say to find the median, all you need to do is to average the bases. Average the bases. The median is the average of the bases. For those of you who prefer equations, we can say this, that your one base plus your second base added divide by 2 gives you your median. That's another way of saying average. Let's try this equation out. Write your equation out the top. Median equals base plus base over 2. I'd like you to write that equation next to every single one of these. Median equals base plus base over 2. Median equals base plus base over 2. Median equals base plus base over 2. Get in the habit of physically writing out equations every single time, even if you know them. We're going to try these together. So for the first one, we're going to do physical pickup. Our median, we're going to circle the word median. This is called physical pickup. You physically circle and pick up and plug in what you have. So circle median. Circle what stands for the median, which in this case is X, equals, you have one base, circle it. Come over here, circle it. Plus the other base, circle. Physically circle. And it's over 2. Now we're going to solve for a median, which is X. So we're going to do 12 plus 26, which is 38, divided by 2. 2 goes into 38. Do the math longhand if you need to. And of course, that's going to be 19. So our median here equals 19. Let's try this one again. And again, I want you to do what's called physical pickup. Write the equation, circle each component, and plug it in step by step. You will cut down on simplistic but terrible errors if you do this systematically. So I'm going to circle the word median. I'm going to come over to my diagram. In my diagram, I am given the median now. That's 24. I'm going to circle base. If one base is x, circle the other base. 35 over 2. Now I want to solve for x. Whenever you have a fraction and a whole number, the easiest way is just to turn that into a fraction, and now we're going to cross multiply. So I'm going to get 24 times 2 equals x plus 35. And we get x equals 13. So we come over here, and x equals 13. Now, you can actually check this out. We know the median equals base plus base over 2. Let's see if this actually works. Here's a way you can check. Our median's 24. We just found one base, supposedly is 13. The other base is 35. We're going to divide by 2. 24 equals, you add those up, we're going to get 48 divided by 2. And 24 equals 24. Check. So it's really easy to check these kind of problems. I would like you to use the technique of physical pickup, and I'd like you to solve for x in this diagram. Pause the video, do your work, and then come back. All right, let's see how you did. Again, we're going to do physical pickup. I circle the word median. I circle my median, and I plug it in. 20 equals. I have one base here. I circle base. I circle my base. 5x minus 15 plus, circle base, 2x minus 8. Of course, the whole thing is over 2. Get this one. I'm going to cross multiply here. And I'm going to get 2 times 20 equals 5x minus 15 plus 2x minus 8. This, of course, is 40, and I'm going to collect like terms while I'm at it. So that's 40. And we have 5x and 2x, which is 7x. And negative 15 minus 8 is going to be minus 23. So here we're going to add 23 both sides. And I end up with 63 equals 7x. We divide both sides by 7. And of course, x equals 9. Let's plug it in. 5 times 9 is 45 minus 15. That's going to get us 30. And 2 times 9 is 18 minus 8. That gives us 10. Let's check. 30 plus 10 divide by 2. That's 40 divided by 2. That equals 20. So you can see when you plug x equals 9, it does equal 20, which is your median. So that's a trapezoid. We have one other shape to talk about today, and that would be a kite. Now, believe it or not, kite is an actual geometric term. A kite is an actual geometric term. It's not just that toy you used to fly as a kid or even now on the beach. So I'd like you to take a look at this. On the left is a rhombus. And on the right is what is called a kite shape. I would like you to answer this question. I'm going to be looking for this when we sign off on these videos. Is how is a kite different from a rhombus? How is a kite different from a rhombus? I'd like you to stop the tape, answer that question, and then pick it up again. How is a kite different than a rhombus? Now I want you to see, how do you think a kite and a rhombus might be similar? This might be easier if you actually draw in the diagonals. Let's draw in the diagonals of a rhombus. This is a rhombus. All four sides are equal. And in a kite, what's different is only the two consecutive sides are equal. Consecutive meaning next to each other. So that would be the consecutive sides. These are the consecutive sides. So in a rhombus, all four sides are equal. In a kite, only the two paired consecutive sides are equal. So if we draw on the diagonals, we know in a rhombus the diagonals make a right angle. And then if you've ever physically made a kite as a kid, you know that those crossbars also create a right angle. So that would be one way that a kite and a rhombus are the same, is that the diagonals are perpendicular. Diagonals are perpendicular. And in a rhombus, the diagonals bisect all the corner angles. In a kite, only what's called the vertex angles are bisected. That would be these two angles are cut in half. The non-vertex angles are not cut in half. So let's explore further what we have here with the kite. So it says right here, here's a kite, and we are told that this segment here is 6, this is 5, and this is 12, and we're to find all possible side lengths and angle measures. So let's see what we could find here. Once you have a right angle, you should be pretty familiar with some things you can do with a right angle. With the right angle comes right triangles, and with right triangles comes all of these. Let's just quickly recap our tools that you can use for right triangles. So with right triangles, we can do geometric mean. We can do the Pythagorean theorem. We can do, if we have them, we can use 30, 60, 90 tables. We can do the 45, 45, 90 tables. These are all right triangle tools. We can use SOHCAHTOA to find side lengths. And you can use what's called inverse SOHCAHTOA, also known as arc SOHCAHTOA, to find angles. So these are all the different tools we can use with a right triangle. So let's see what we can work with here. We see we have two sides of a right triangle, which means we can use the Pythagorean theorem. So right here, I'm going to go 5 squared plus 12 squared equals my unknown squared, which is my hypo, because there's my right angle, squared. This is 25 plus 144 equals my hypo squared. Add them up is 169 equals hypo squared. And I can square root both sides. You should recognize 169 as a perfect square, so it's 13 equals my hypo in this case. So I'm going to put a 13 there. And we know the consecutive sides are equal, so this is also 13. Knowing this, I can go over here on this side, and I can do another Pythagorean theorem. So I can do 6 squared plus 5 squared equals this hypo squared. This is 36 plus 25 equals hypo squared. I'm going to add 36 and 25. You get 61 equals hypo squared. We're going to square root, and it will round to the nearest tenth here, so I'm going to do 61 square root, and I get 7.8. So this is 7.8, which means this is 7.8. We also have right angles in here. Now, we have no other angles except the right angles. But let's pull out what we do have. Let's pull out this triangle here. We have a 5 and a 12 and 13. And if I want to find this angle right here, here's opposite, adjacent, and hypo. I could actually use any one of them, sine, cosine, or tangent. I'm just going to go ahead and use sine because that's what my eyeballs pick up the easiest. There's OH, so I'm going to do inverse sine 5 over 13, and that's going to give me my angle theta right there. So I'm going to do 5 divided by 13, inverse sine, and I get 22.6 degrees. And with this, I could actually find everything else. Let me show you how you can do that. With one tiny little angle, you can find everything else. That's 22.6. And the vertex angles are bisected. This has to be 22.6. And since triangles add up to 180, if that's 22.6 and that's 90, we can find that just by doing 22.6 plus 90. Take it away from 180. And we're going to get 67.4 here. That means this over here is 67.4. Now, warning, this is not 67.4 over here, so we have to use SOHCAHTOA again to find an angle. So to find this angle, I'm going to go this way, opposite, inverse sine, -1, opposite, which is 6, over my hypo, which is 7.8, and that's going to give me this angle up here. I'm going to go 6 divided by 7.8, inverse sine, you get 50.3. That's 90 degrees. We're going to take 50.3 and we're going to take it away from 90. And we get 39.7. That means this is 39.7 degrees. This must be 39.7 degrees. That means this is 50.3. So we used in this kite, because we have right angles, which gave us right triangles, we used both the Pythagorean theorem and we used inverse SOHCAHTOA to find the angles. So once again, right triangles, come back and strike revenge. Do not forget those right triangle tools. You will use them frequently for the rest of the year.